adaptive sparse recovery with limited adaptivity, meaning that you have just a few rounds of adaptivity. Also, same problem as doing multi-pass heavy hitters in a turn-to-cell stream. So, I need new batteries. All right. So for the talk, I'm first going to just describe the problem. Then the k equals 1 case is what we already know, we've known for years. And I'll just explain how the algorithm and the lower bounds work for that. And then the goal of this talk is to extend this to learning multiple coordinates, higher k, and we'll give both a lower and new upper bound for that. So in general, we're talking about sparsity. So a vector, the same problem that Piotr was talking about. If the most frequent coordinates appear much more often than the less frequent ones, then in order to estimate the vector, you only really need to find those large coordinates. And so our hope is to find a vector that is close to this approximately sparse vector. And it's approximately sparse because it has maybe a power law Zipfian distribution. And so, for instance, if I want to estimate an image, this image is not very sparse. But if you take it into a different basis, like the wavelet basis, then this is some recursive thing where large coordinates correspond to edges. And so in this other basis, images do tend to be fairly sparse. And so lots of data has sparsity in some basis. And the goal is to use that structure of your data to estimate it well. So the sparse recovery or compressed sensing problem, which for turn-to-cell streams is almost equivalent to the heavy hitters or the frequency estimation problem, is that you have some vector x and you know what basis it's sparse in, but you don't know what the vector x is. And instead you can see linear measurements of it. So why are linear measurements interesting? It's because in lots of different modalities of access to your data, it's sort of easy in hardware to get these linear measurements. So one example is in genetic testing. You can like this, a simple genetic test, you like take a drop of somebody's blood and you measure, do they have this disease? But you could also mix together different people's blood and then you get a linear combination if you measure how much of the mutation is in this blood. And so in genetic testing, you can get a linear combination. In routers, you can store AX, and then when a new input comes, like a new IP address, that just affects one coordinate of X, and so you add the corresponding column of A, so you can store A times X plus delta as just your previously stored value plus A times delta. And so you're storing this lower dimensional thing, and in some single pixel camera, you put a filter in for the lens. And so there's lots of different places where you can do linear measurements, and the question is how useful is this? And so the goal here is to get close to find X. And there's lots and lots of papers on this. And one formalization of this problem is that we're going to choose some distribution on matrices, on your linear sketch matrices, and then you give in AX, you want to estimate X. And we'll say that the error in your estimate is proportional to the distance from X to its nearest k-sparse approximation. And so if you have a Zipfian distribution, then the largest coordinates are large, and after you drop the top k, they're very small. So if it's 1 over I power law, then this L2 norm converges, and you get very good error in estimating the coordinates. And this is standard non-adaptive sparse recovery. What we're going to talk in this talk is adaptive, which means multipath. So instead of standard sparse recovery, we can do it in k log n measurements. We're going to choose a first matrix, A1, CA1X, and now we're going to choose A2X, choose A2 and CA2X, choose A3 and CA3X. And so in all of these, in many modalities, it makes sense that you can do this. But often it's costly. And so you want to minimize the number of times you need to go back to your input and measure it again. And yes?
Do you want to do proper recovery, meaning x hat is supposed to be k-sparse? Or
so if your c is just a constant factor, it doesn't matter. Because you can take whatever your output is and take the top k, and then it'll just lose a factor of 2. If you want 1 plus epsilon, then you get different answers depending if it's proper or not. And the dependence on epsilon, but for this talk, we're not going to care about the epsilon dependence.
Question?
Yeah.
So the example of the packet routing or streaming,
Yeah.
how does this...
Right, so it wouldn't. So you can't do that if it's truly streaming. But if you have, say, often you use streaming algorithms because you're streaming it from where it's stored in some data center. Right, if you're using it for MapReduce or using.
For the router example.
Right, so for the router you can't do multipass. But for other applications of streaming algorithms, you can do multipass, but it's expensive and you don't want to do 100 passes. You'd like to do maybe 2 passes, 3 passes.
Now I'm just confused because as you're processing the data, a new item comes, but what have you stored previously in this way of...
Right, so in 1 pass you can't, this is not for 1 pass algorithms.
Oh, got it.
This is for multipass algorithms. And so the question is, if I can do a 2-pass algorithm, does it take k log n linear measurements? Right, we know that a 1-pass algorithm requires k log n linear measurements, so what happens with the 2-pass?
Okay.
And so some work I did in grad school with Piotr and David is we showed that if you can do many passes, so if I don't care how many passes I do some order log n times log star n passes, then you can decrease this from k log n linear measurements down to k log n measurements. But this wasn't for limited adaptivity. So this is one result. There's many other results in adaptive recovery. So if you care about the dependence on epsilon, then the first work said, okay, we'll take the same number of measurements as you require non-adaptively, and we'll show that you can get a better dependence on epsilon. So first couple works looked at k equals 1, and then they were able to generalize it to general k. And then we looked at it and said, actually, you can decrease the number of measurements. And a recent result by David and his co-authors shows that in fact you can separate the epsilon and the n dependence, so that you can do it in basically k over epsilon plus k log n. This is the upper bound.
This is with many rounds.
This is with many rounds. That's right. So this is again with like log n times log star k rounds. And then the lower bounds, so Airy and Kendison Davenport, I don't know if Airy is here, showed that you can't improve the epsilon dependence, that you need k over epsilon. Maybe you can remove this log 1 over epsilon. And then we showed for k equals 1 that you need log n. But this leaves the question, can you separate the k and the n just as you can separate the epsilon and the n? And so this is where we were stuck for a while. And so just to review, we knew that the optimum for constant epsilon was between k plus log n and k times log n. And the question is which. And so what we're able to show here, and I guess for constant r, then you can do the k equals 1 version in log to the 1 over r. And so you can get the lower bound is k plus log to the 1 over r. The upper bound is k times log to the, 1 over r minus 3. So this is another recent result by David and others. The same one that got the separate epsilon n. You could instead of separating epsilon n, you could decrease the number of rounds to only have 3 extra rounds. And so what we show is for constant r, the lower bound is k times log to the 1 over rn. So you do need to have this relationship. And the upper bound, you don't need the extra rounds with some log star k excess number of measurements. And this comes from what we know how to do for non-adaptive high SNR recovery. And if we could remove that, then you could remove the log star k here.
Is the log star k inside the log 1 over r?
It's not inside,
Okay.
but I mean, log star versus log star, not a big difference. Right. So, but there is a caveat here, which is the lower bound only applies if k is relatively small. So rather than k equals 1, we can do it up to 2 to the log of the 1 over r, which if you think about it, that means you can get this bound if the bound you get is bigger than k log k. So it's if, so if r equals 2, this is saying if k log k is less than k root log n, then it requires k root log n measurements, even in 2-round multipass streaming to do heavy hitters. Okay. Yeah.
Are these bit complexity lower bounds?
These are row complexity. We're just caring about linear measurements here.
So they don't give you streaming lower bounds, right?
So I haven't thought about getting them, so yeah, I would not, yeah, I haven't thought about it. Yeah.
Trying to compare the two, what exactly seems to break down when you go above super constant rounds?
So, I mean, our algorithms, so the lower bound, it works largely for super constant R. It's just that the bound you get, this log to the 1 over R, is going to become very small. And there's some polynomial in R dependence. So you can get something, but it's a little bit hard to describe what you get. For the upper bound, like the way we do it has, I think, an exponential in R dependence. And so, yes, you can get something for super constant R, but again, it's not very good. Yeah. And then and then above this caveat, this threshold of k log k, or 2 to the log of the 1 over Rn, as long as you're less than n to the little o of 1, you still get something that's bigger than k. So you can't suddenly separate k and n when you go to high k. But we don't have the type bound. Yeah. Okay, so to understand how this works, let's first think about the k equals 1 case, because that's the one we actually know how to do. So in k equals 1, the theorems that we had like 6 years ago showed that it requires r times log to the 1 over Rn measurements in Rns. And so first we'll see when r equals 1 why it requires log n measurements. And then we'll see how you can break this if you can do adaptivity. And then we'll see how to extend the lower bound to get the log n. So the hard case, in general, the hard case for all of this talk will be that you have a single coordinate that's 1, and every other coordinate is going to be Gaussian. And the Gaussians are going to be fairly small, and so the L2 guarantee requires you to be able to find this coordinate. Right? If your Gaussian is less than 1/10, then a 3 approximation, you still need to find that coordinate, because it's really, really important. And so this coordinate is at some position z. There's n possible positions, so you need to learn log n bits to describe z. And yet the observation, right, v dot x, I can choose any vector v. I get v dot x, which is v sub z plus v dot this Gaussian noise, which is itself just a Gaussian. Right? So you're going to see v sub z plus some scaled Gaussian, where this scaling is also dependent on the norm of v. And so what does that mean? That means for some z, as a function of the Gaussian noise, I'll get some Gaussian. For a different z, I would get a Gaussian centered at a different value. The other v sub z, a different z will get a different value. And so the situation you'd be in is, well, I get a sample from one of these, I need to figure out which one they are. And so you can distinguish a few of these, but if there's too many of them, then you're not going to really be able to learn that much information. And so if you think about this, this is the additive white Gaussian noise channel. It's a classic. This is what Shannon analyzed in 1948 when he invented information theory. And he showed that the information capacity of this channel is bounded by the log of the signal-to-noise ratio, where the signal-to-noise ratio is the ratio of the variance of the signal to the variance of the noise. What is that? That is the expectation of v sub z squared divided by v2 squared over n because of the scaling in. And that, well, z is random. So that's just 1. And that says that your signal-to-noise ratio is constant, and so the amount of information you get in any single measurement is constant. But you need to learn log n bits to find z, so it takes log n measurements if you're doing them non-adaptively. So the question is, how does this change if I can do, say, 2 passes? Or I can do many passes? In the first round, it's still true that you only get 1 bit per measurement. But in the later rounds, you have some information. Right? And what does your information say? It means that in the later rounds, conditioned on what you know, V and Z are not independent. There's going to be some dependence because I know something about Z when I choose V. And so it's still true that I can get only log of the SNR, and my SNR is the ratio between the expected value of V sub Z squared to the norm over n, but now that expectation is not 1. And as we learn about where Z is, we can focus our measurements on those positions. We can learn more information per measurement. So to see how this could work, we start out, we don't have any idea where it is, and so we could set V, say, to be -1 on the first half and 1 on the second half of the input. And then we would get a sample from like one Gaussian or the other, and so we get maybe 1 bit of information. Right? If we get something on the left, we figure out on the left. If we get something on the right, we figure out on the right. But now we can restrict. We know that our measurement is in some subset, so we can set V to be 0 everywhere else. So we get the same amount of signal, but we get 0 noise. We'll get much less noise because we're going to groove this half. And we can learn more bits. And so then, as we do this, once we've learned B bits of information, we're going to be restricting the signal to an n over B size region, which means we're going to get rid of n over 2 to the B size region. So we're going to get rid of most of the noise. Our noise is going to go down by a factor 2 to the B. And so we can fit in about 2 to the B Gaussians and still identify them. And so if we've learned B bits of information so far, we can get another B bits of information in a single measurement. So information is growing exponentially. In log n rounds, we're going to be able to get log n bits. And that's the idea. And so it goes very, very fast. And if I just have 2 rounds, then I learn 1 bit per round per measurement in the first round. So I do root log n measurements in the first round. I learn root log n bits. And now I can learn root log n bits per measurement. I do root log n measurements. I can learn log n bits. And so that's how you get the root log. So this is the upper bound. Now how do we get a lower bound? So what we'd like to say is at every stage we have some posterior p on where Z is. And this reflects having learned B bits of information, which is how much the entropy of P is less than log n. And the lemma that one can show is that now, whatever V you choose, the mutual information between the measurement you get, V dot x, and where Z is bounded by B plus 1. And so how do we do this? Well, again, our mutual information is bounded by that Shannon-Hartley. But now, because we can choose V and P is not uniform, this would be about 1 plus n times the maximum value of P. Because we could choose V to be entirely on the largest value of P. And so if P were roughly uniform, then this would be about n over 2 to the B. This would give you the right bound of B. The problem is this is much too weak when your distribution is non-uniform. Basically, the Shannon-Hartley theorem on capacity is only accurate, like it's tight, if the signal you send is a Gaussian. And if it's very much non-Gaussian, then it can be very inaccurate. And so what we need to say is we need to get something better if we have a very skewed distribution for P. And particularly the way we're going to do this is we partition P by the level sets. So the level you're in says that you're about 2 to the j factor larger than knowing nothing. And you can show that the expected level that you lie in is B. Right? So you could always be in coordinates of value 2 to the b over n. That would be just a uniform distribution on n over 2 to the b things. Or you could have a much smaller chance of being much larger. And then we can bound the mutual information by the mutual information conditioned on what level you're in, plus the entropy of finding the level you're in. And then Shannon-Hartley can show that in any given level, your mutual information is bounded by the L infinity norm of P in that level, which was 2 to the j, and log of that, so you get j for any given level j. Because the expected level is b, this would give you order b as the mutual information. And you can also show that the entropy of the level is b, and so overall you get the mutual information per measurement is b. So this is the key level. Let's you solve it for k equals 1. And the question is, how do we extend this to general k? I guess let's just give it up. So this says that, suppose I have 2 rounds, learn order m bits in the first round, order m squared in the bits. In the second round, therefore m needs to be at least root log n. And in general, you get the bounds that we described. So what happens for general k? So let's take the proof outline and see how can we extend this to general k. So we had a single coordinate plus noise. We take our posterior that has b bits of information, and we showed this key lemma that the mutual information in any new measure, the amount of information you get from any new measurement is order b. What happens for general k? Well, the natural thing is to just take k independent copies, right? We want to say that doing k, it takes k times more information, and so we'll just take k Gaussians, or k coordinates within Gaussians, extend our domain by a factor of k. Yeah, so we can formalize this. So now instead of having a single z, we're going to have a k tuple of z's. We have some posterior from the previous measurements, which have some information content, which is now not log n minus h of v, but k log n minus h of v, because that's the posterior is over k tuples. And the question is now, what lemma do we want to show? Right. Previously, we showed that the information was b plus 1. Given b bits, you can learn b bits. But what do we want now? So a natural thing would be to try just the same bound. That the information is still just b. And this is true. You can show it, but it's not good enough at all. Right? Because then we get k log n to the 1 over r instead of k times log to the 1 over rn. We get log of k log n instead of k log n. And so what we want to say is something like, given k b bits of information, I can only get about b over k bits about each one. And because each coordinate, the average coordinate, I'll only have b over k bits of information about it, and that can double. The problem is that this bound isn't true. It's false. Because I could start out only learning the first coordinate. And I know I can learn, if I learn log n over 2 bits in the first coordinate, then the next round I can still learn log n bits. And so it's just not true that the amount of information that I learn in a single measurement can be b over k. But if you think about it, that example is saying that there can be some coordinates that so far you've learned much more than average, and then in the next round you're going to learn even more than average. So maybe you can throw out the coordinates that are too large. And so if I just apply Markov's inequality, I could hope to say maybe most of the coordinates, 99% of the coordinates, only have order b over k bits of information about them, and therefore on those coordinates I'm only going to get order b over k bits of information. And this is one reason you would require r to be constant. Because if I throw out a constant fraction at each stage, I can only set r to be constant. And so this would be the goal maybe. We'll find some subset of coordinates and say that the information about them is only order b over k. This would be strong enough for constant r. And it's true if your distribution is a product distribution. That is, if your information is independent about each of the coordinates. But there's no reason that needs to be true. And in general, this is false. So if I knew something correlated about my different coordinates, say I knew that the parities of the indices were all the same, then I can make a measurement that gets a lot more information than you would expect from this. Right? I can learn about everybody. Yeah?
So But can you make your original, the hard distribution you're creating, are there on disjoint subwords of size n over k?
They are, yeah.
And then because they are independent of each other, the information you get for each one is going to be divided by the factor k on average. No?
But I don't know how to, like maybe you could show something based because you've had linear measurements, but they can be correlated information. If I give some linear measurements, I'll learn something about what's happened, but it can be correlated information. And so I can have some correlation structure on my posterior distribution on the coordinates. And I don't know how to describe it other than say that you only have b bits overall. And so what we're going to get instead is b over k plus log k bits. So that this correlation structure can give you more information, but only up to a log k. Right? K of them, apply Cauchy-Shorts and lose a factor of k. And so this will be true, and it's strong enough if the log k doesn't matter. And why wouldn't the log k matter? It wouldn't matter if b over k is bigger than log k. And so in the first round, you don't need this, because it's not adaptive, you know it's uniform, you only get constant. And so as long as by the second round, you've already gotten k log k bits, then the log k don't matter, and this is what you need to get what you want. And so that's why we're going to have that restriction that k log k is less than m. So how do you prove this? Well, again, apply data processing and Shannon-Hartley, you get some log of the signal-to-noise ratio. But the signal-to-noise ratio is now the expectation of the sum over my k coordinates squared, of their values squared. That's a little annoying, so we apply Cauchy-Shorts and change the sum squared to the sum of the squares, losing this factor of k. And now this is really an average over the different chunks of what their signal-noise ratio is within that chunk. So you can have your measurement that has some in chunk 1, some in chunk 2, they're just the average of the signal-noise ratios. And so as long as no chunk has too high a signal-to-noise ratio, this will be bounded. And so we want to say that we can find a large subset of coordinates such that that they all have bounded signal-to-noise ratio. And as we saw in the k equals 1, there's this other issue of the level sets. And so instead what we have is that on average over all coordinates and over the level set that you happen to lie in, this log is going to be bounded. And so we have some situation where there's many coordinates and the x will happen to lie in some level set here. And most of them are going to be good, meaning the information about that coordinate in that level set is order b over k, but some of them are going to be bad. But usually you're going to be able to find some large set of coordinates that are good. And so 99% of the time you're going to find that 0.99k such that the maximum SNR is bounded by b over k. And so that gives us the key lemma that we need, which is now a little bit more awkward because we're going to say we can get b over k plus log k per measurement plus an additional b plus k factor, which comes from this h of j term, if you recall from the k equals 1. The entropy of your partition is now b plus k. And so if you look at how is this done in k equals 1, you said that the information was bounded by the information condition on j plus h of j. The information condition on j was order b plus 1. The entropy of j was b plus 1. And now you do the same thing, except this is now SNR log of the SNR in the union, which is bounded by k times the maximum, which is bounded by b over k plus log k times plus b plus 1. And so then what we say is the first round is non-adaptive. We only learn order m bits. In the second round, we can learn m times b over k plus log k plus b plus k. And so if your number of measurements is larger than k log k, the dominant term is mb over k, giving you m squared over k bits. And so since you need to learn k log n bits, this means m needs to be at least k root log n. And so the big questions here are, first, can we avoid the restriction on k? And so as when we wrote this paper, we didn't really see how to do it. When I was preparing this talk, I realized another option for that key lemma that I think might make this work, which is to look at the mutual information conditioned on the coordinates that you throw out. And I don't have a counterexample to this being b over k plus 1, and this would suffice. And then a separate question is get a better dependence on r. So as r goes to infinity, then we don't know how to say anything because of this entropy of the partition, meaning that every round we could get a lot more information. So that's the lower bound. Any questions here? I'll go briefly over the upper bound. Oh, Jerry.
You're confused. Do you get something for super constant r for the lower bound?
You can get something for very slightly super constant r, right? You can look at the paper to see what the dependence is, but not for large r. So for the upper bound, again, we have the optimal one sparse recovery algorithm. And we want to turn this into a k-sparse recovery algorithm. And there's a standard way that happens in a lot of papers for doing that, and has 3 steps. First, you throw your coordinates into buckets. Then in each bucket, you try one sparse recovery. If there is exactly one heavy hitter and not too much noise, you'll find it. And then that'll get you 90% of the heavy hitters, and you clean up the mistakes, either by recursion or some other technique. And the problem is these extra steps, they add rounds. They require doing something new with new rounds. And so in Price-Woodruff, we did set 3 recursively, and so that meant that it took log star k recursive rounds, and so the number of rounds blew up by a factor of order log star k. Bakoshi and Woodruff improved this to being only 1 round at the beginning, 2 rounds at the end. But it still means that you have 3 extra rounds, and so if I want a 2-pass algorithm, you can't get anything. And so the question is, how can we avoid these extra rounds? And so we're going to do a different approach, which doesn't look at the k equals 1 case. Instead, it's going to reduce to higher signal-noise ratio k-sparse recovery, which we know how to solve in nearly optimal k log base c of n rounds. So the basic approach would be we throw into k times 2 to the root log n buckets. And now I do k-sparse recovery. This takes k log n over k is k log 2 to the root log n is k root log n measurements. And then now that I've restricted to this much smaller subset, right? So now I've thrown out most of the coordinates because they'll have landed in a different bucket. And so the coordinates that remain will be enriched. They'll have much higher signal-to-noise ratio, and so I apply high signal-to-noise ratio. C equals 2 to the root log n, sparse approximate recovery, k log base c of n, which is, again, k root log n. And so the overall number of measurements is k root log n. The problem is that I can't miss anything, because my goal is to avoid having to do this cleanup round. And so I need to ensure that this k-sparse recovery in this projected domain doesn't lose anything important. And there will be collisions. So even if things collide, I need to find that bucket to know that its preimage is important. And so we have this technique of triple Gaussian hashing that does it. So for intuition, suppose my vector looks like this k-sparse binary plus a little bit of Gaussian noise. And it's very small so that you need to find almost every coordinate. So given some partition, throwing it into buckets, the question is so within a bucket, there's many coordinates that are supposed to go there. How should I combine them to get this lower dimensional vector? So the most common technique that you see is to do it with random signs. So I set y in a given bucket to be the sum over everything that passes to this bucket of the value times the random sign. And so just as a picture, if I take this and I do this sign projection, I get this value. And if you notice, there's 3 coordinates here. There are 5 coordinates here. What happened is 2 of them land in the same bucket. and they happen to have canceling signs, and so you got 0. And so you're not going to find them. And so this means that you're not, even without noise, the sign projection doesn't work. On the other hand, even with noise, it doesn't do much worse. Because if you hash, if you don't collide, you're going to be pretty big. And so the noise doesn't mess you up very much. An alternative solution would be to use Gaussians instead of random signs. If I do it with Gaussians, then when I do it without noise, I'm in good shape. You'll see this coordinate didn't appear here, it appears here. All the entire image of the heavy hitters will appear just because a real number isn't going to be 0. Problem is now large values can become small, and so with noise you're not going to be able to find this coordinate. So these small coordinates, you can lose something with noise. And so the approach we have is just choose 3 different Gaussians. It turns out 3 is the right number. If I do 3 of them, then sure, you can miss a coordinate, a bucket in one of the hashes, but the chance that you miss it in 3 hashes is pretty small. And it gets smaller the bigger, the more important it is to find a coordinate, because the bigger it is, the less likely you're going to miss it all 3 times. And so overall, the expected mass of the false negatives is order the noise level. And so it's fine to miss. And so you don't need to do any cleanup round. And since you don't need to do any cleanup round, you get k log to the 1 over r n. Yeah?
Why 3?
Yeah, so if you think about this example, where you just have binary. So we don't know what the sparse recovery algorithm will do. It could say drop the smallest heavy hitter images. And so it can, okay, so the image of a coordinate has a 1 in k to the 1/3 chance of being less than k to the 2/3. And then you can miss all of them. And so you can have a 1 in k to the 1/3 chance of missing one of these binary values. And so with 3, that becomes 1 over k, and so you miss on average 1, which is what this noise level tolerates. Yeah. And so this is the key idea that lets us get the nearly optimal, and so we get k root log n times log star k for r equals 2. Okay, so yes?
What is wrong with doing 3 attempts of sine?
So with sines, it's not going to work because without noise, you can't miss anything. And, right, so this coordinate has 2 heavy hitters in it. If I tried it 3 times, there'd still be a 1/8 chance that I miss it entirely. And so you need to be that you miss nothing if there's no noise. And with Gaussians, you miss nothing if there's no noise.
Use 3 different Gaussians, but the same hashing.
The same H, that's right.
The same H.
Yeah. You could try different H's, but even so, you don't want your buckets to be much bigger than order k, and so you still would have a constant factor of missing things with signs.
Yeah, no, I missed that. That's
Yeah.
subtlety.
That's right. Yeah. Okay. So, just to summarize, previously it was k plus root log n as the lower bound. Now it's k times root log n as a lower bound, at least if k is not too big. And the upper bound avoids the extra passes at this cost of a log star k, which will be removed if we can improve C approximate recovery for high C. And there's lots of open questions, as you can see. I think the biggest one that at a conceptual level I don't know how to approach is to say, as if R is really unlimited, like bigger than k, then you can't do any better. And right, I could imagine that these techniques might improve to R being like log n, but above that, I don't know how to get it at all. Thank you.
Any questions to Eric?
I have a orthogonal question. So in your paper with Bora, Dimakis, like you you studied what happens if you do random measurements on what the prior generated by GANs, right?
Yeah.
Do you have a sense if in that case adaptivity would help? I promise it's orthogonal.
Yeah, so this question is, if you don't have sparsity, but you have some other structural assumption, then can you benefit from adaptivity? And my guess would be that it depends a lot on the structural assumption that you have. That in the generality we had in that, so Peter was referencing a paper on if you know your distribution comes from the output of some generative model, like a GAN, then you can get something very generally, and I doubt you can get something general.
So I have a question here about the Gaussians. You just mentioned like 3 Gaussians. Is it really important that it's Gaussians, or would you just really use like properties of Gaussians, or just like uniform would be equally good? You just want to break out.
So we use the property that.
Anti-symmetry.
So we want it to be the case that when you have collisions, that only helps. And so if I have collisions, then it's just going to be more likely that I find that coordinate. Now, by the central limit theorem, things are going to converge to a Gaussian. So yes, probably if you did random uniform between -1 and 1, it would work. Like really. Okay,
Are you using like stability or something? No.
We do use that. But what we really need is anti-concentration of some of the sum. So because it's stable, the sum is a Gaussian, so it's anti-concentrated. But you could have other distributions and they would still anti-concentrate.
So thank you very much. We have a break until 11:30.